thanks everyone for coming. So this, we're kind of calling them lightning talks. The idea is not necessarily to be that duplication of the graduate student talks that you've seen in previous seminars. It turned out this way that as graduate students, but we want to kick off and start getting in the habit of letting other people within the center know about the research that's going on. So one of the ideas that has been proposed is to include maybe a 10-15-minute presentation in the general meetings so that we can start to get a little bit more of the exchange of ideas among all the different groups. So the idea, since unfortunately our speaker for today had to cancel earlier in the semester, was to use this as an opportunity to kick that off. So with that, we've got 3 presentations from multiple different individuals. I'll introduce the second 2, but I'll let you, Sean, introduce yourself.
So, and we have one from each of the colleges.
Yes, we did.
Pretty cool.
That was intentional, yeah.
Yeah. So our first speaker is Eric Hiatt. He's a PhD student with Marquesa and I in the Jackson School, who's been working on basic groundwater problems on other planets. And I think we're going to hear an update from his Lunar and Planetary Science Conferences talk. And Eric was an undergrad here and has been doing his PhD with us. Before that was a combat veteran.
Yep. All right, thanks, Sean. Yeah, today I'm going to talk about the climate of early Mars and how global groundwater model-based constraints can help us understand the climatic optimals that produce the geomorphology we see. And acknowledgement to my team there, along with Sean and Mark. I must work with Tim Gouge and Mohammed Al-Shadab. To say anything about Mars's climate, we need to understand a little bit about the geologic history of Mars. On the right, you have your laser altimetry map.
Collapse the.
Yes.
It's probably on the computer in the room.
It's on that. Yeah, there you go.
Gotcha.
Perfect.
Okay, on the right, we have a laser altimetry map, it's nothing more topography. On the left, we have Mars fluvial history from Carr et al. And now what we can think about this planet is a kind of a tale of 2 planets, right? You have the early times in the Noachian, which is equivalent to the Hadean time on Earth, where you have hydrous, close to terrestrial amounts of erosion. You have production of biosilicates, pH kind of like Earth. Then you desiccate, and all of those erosional events are rare, few and far between. But that's good for us because it preserves that ancient crust. It preserves the crust of 3.7, so we can look at it and say something about Mars's ancient past. And in that past, we have these things called the valley networks. And this is the Noachian train, the oldest train on Mars. And it records evidence of incised fluvial systems that are weakly integrated, showing clear signs of surface water processes. Also, we have this area in the Arabia Terra. These are called the light layer deposits, and they're believed groundwater upwelled. I'm going to use the term upwelling. This has a connotation of a distal recharge of an aquifer and a proximal upwelling due to that recharge. And here we think that this is thought to be produced by fluctuations of the groundwater table that then evaporate and you leave evaporative deposits. Notably, it's one of the few places on Mars that has an actual depositional environment on a regional scale. That's going to be an important constraint, but the biggest constraint on our model now is going to be the area in the Noachian Terra. These are called the valley networks. They're a network of incised channels that go between craters, and they incise downwards up to 1 kilometer and can run tens of thousands of kilometers long. And why is this important? Well, the depth to which a system can incise to is often set by the groundwater table. And if you think about the Grand Canyon, it's cutting because the water table is below it. In Florida, you can't form a Grand Canyon because the water table is right there. And so we know that over geologically significant times, groundwater did not get above the elevation of the floor of the valley networks. And so Mars also has this 2-part history in its topography, right? You have a large basin forming events. This is co-evolved with late heavy bombardment or that tailing, whichever you prefer. But it sets up, where you have these the crustal dichotomy, up and a down on Mars. The crust is about half as thick up there, and you have a 4-kilometer drop off. Along with Hellas and Argyre, these are very large basins that control the hydrologic system. And so why else do we care? This is getting into a habitability talk, care about the environment, the climate, but also groundwater is important for habitable environments as well. People believe that these impact craters had hosted huge melt sheets, which can approximate a mid-ocean ridge spreading center where you have a redox environment, element cycling, heat, time. And so we want to think about climate, and we want to think about habitability. And to do that, I have this little illustrative figure here, where we've taken a regional groundwater system and plotted it. What you see, the blue going left to right is hydraulic head gradients. The hydraulic head is just the groundwater table elevation below above a dam, so just the top of your water table. And you're going right to left downhill. The red lines are streamlines where you have equal flow and you streamline. And now where those streamlines are bunched together, you have higher flow, and spread out, they have less flow. When we impacted it with those circular impactors, creating more conductivity. A large impact crater can actually greatly alter this regional flow. And here you can see it with areas of significant alteration. We have flow into this crater, and we can keep playing this game, saying how big of an impact would it take to actually advect material from one crater to another. And here I've set it up to where you're actually going up regional gradient. But so it's obvious that this background gradient, the global scale gradients, are going to be very important to allowing us to either move things up or down. And so that's where we want to start. We want to start at a global scale rather than a regional scale. And so you might ask me, like, has this work been done before? Yes, there's global scale groundwater models on Mars. The issue with those models is that they could not have standing bodies of water. And then, so the recharge, the precipitation was tied to how much water came out of the ground that could then get evaporated and redistributed. And so we want to be able to understand how these large impact basins could actually affect the global scale gradients and how we could use those to say something about the climate. To do that, we're going to use what's commonly used in most proprietary softwares like your mod flows and things like that, is the Dupuy-Forchheimer approximation. This takes the gradient of the height of the, this takes the divergence of the hydraulic conductivity kappa times the head, the hydraulic head, that aquifer height level, times the gradient at the head, and it's equal to the recharge. And to do this, we discretize it on a spherical shell coordinate system so that your you're using rhumb lines as great circles instead of rhumb lines, so your geometry is correct. We have a Newton-Raphson solver because the divergence of the head times the gradient of the head is a nonlinear problem. So we have an iterative solver. We have harmonic boundary conditions. This means nothing more than you wrap the boundary conditions on top of themselves. Like if you go over the pole, you're just going on the other side of the pole. If you cross, where those boundary conditions are on the globe, just go to the other side of the globe. All right. And then what makes our model different is our ability to have a dynamic domain. And so here I took that largest impact basin named Hellas and outlined it for you. And we can actually identify the cells that are internal and external to any given shoreline. And the idea here, you assume that body of water is an equipotential surface. And then you can just create a boundary condition there on those the black line or the black cells. And we can solve for the hydraulic head by after removing that basin. And so we did this in work that we just recently published. We set the parameters equal to this. Recharge is 0.01 millimeters per year. Conductivity is 10 to the -7th. And we recharge 45 to 45. And you ask, what happens when you change these parameters? There's actually the whole first half of that paper is dedicated to nothing but a sensitivity analysis. And if you don't believe me, it's actually quite impressive how little it varies when you change wholesale large things like where your shoreline's at. And so we went ahead and we're going to look for recharge here. We can have upwelling there in those light layer deposits. We don't want to see any recharge or anything upwelling there. And here on this map, I should say that the red is, I've taken the subtracted topography away from the hydraulic head once we solve for this. So we parameterize it like that. We solve the steady state, and I subtract the topography from the top of the aquifer. Anything in blue, the water table is above the ground, which is great there because I set it above the ground. And the red is below the ground. And you can start to pop out of the groundwater, the topography there where you get those yellows and whites. And now this is not widespread. You do see pretty widespread like layer deposits. So we want to keep playing this game, right? How much can we raise the recharge by? So we did that. And that's what you get at 0.03. And that's actually kind of what you see geographically distributed on Mars in the geomorphology. So that's great. That's the valid solution over steady state. But just at 0.1 millimeters per year integrated over geologic time, you start to flood out 60%, 50-something% of the planet, which is not geologically plausible.
What is a recharge rate?
So there's a partitioning. Great questions. Thank you. Precipitation falls, and then you partition it into either runoff or recharge. So you'll infiltrate some, you'll run off others. And so the recharge rate isn't the precipitation, but it's how much is getting into the groundwater. Thank you. So we want to compare this to literature, right? We have on your y-axis is the percentage of the highlands that's upwelling, that blue part of the last figure I showed. And on the x-axis is recharge in millimeters per year in log scale. And then we have the blue is precipitation estimates. These are done by like geomorphic people who say it takes X amount of water to cut a valley And then you can think about like that partitioning that I talked about. The lighter blue is basal snow melt rates of glaciation, because some people think Mars was cold and arid. And then there's direct recharge modeling work in the brown. And I can remind you that those are our three scenarios that I had there, and you can see that they all fall on the very low end of what literature suggests are plausible values. And so we want to think about what's happening there. And so one is that there's an up and a down to Mars, right? And I told you about the dichotomy, and it comes out to this dimensionless ratio, recharge over conductivity. And it's roughly that. So even any transient model you have, the integrated amount of recharge over time is going to cycle around that 10 to the negative fifth. It's just so large, right? You can only rain so much. If Earth, the only basin on Earth was the Mediterranean, there's only so much you can rain in North America and Africa before you start flooding that out. And that's just a byproduct of having this global dichotomy on Mars. The other thing is maybe Mars is water limited. And that means like when you form these big basins, you're storing water and there's not enough that comes to the surface to evaporate and form precipitation. You could have a system that's actually it is runoff dominated. It's like a sob cut thing. You know, you stick a sponge under a faucet and it takes a minute for that to sink in before it wets. And so when you have these ephemeral events, most of it's probably going to run off. It's also, it could be that the transient response to the aquifer is slower than the duration of the climate excursions. And I'm going to get into that a little bit because that's how we can tell something about climate. And it's likely a combination of all these things. So, what we have here is I have the Mars surface that's azimuthally averaged. The gray line, am I over?
2 more minutes.
Oh, okay, gray line, okay. So this is fluctuating the aquifer on Mars. We recharge, water pops up, water goes down. And so we want to know how transiently we can do that. So I've made this model. We got 1 centimeter per year, 6,000 on, 200,000 off, 12,000 on, and we're looking at those areas. And the top is just the hydraulic head, and I want you to look at how slow that diffuses. And then we're going to do a blip here. And you can see how quickly it actually goes up and slow to diffuse away. And that's just a long time scale of diffusion due to the long distances. I did another model. This is an accident. I left it on accident. And you can see how quickly the entire planet floods out. And so these duration events of these climate optimals have to be very, very, very slow. The periodicity has to be very long. Yeah, it just floods out like a chain. All right. And so the next thing I have to do is transient shorelines, because we're not moving those shorelines. We want to see how I'm not balanced right now because we need to be able to pull those shorelines back to keep water equilibrium. To do that, I need a bunch of shorelines that I can calculate the volume of and then calculate the flux in between. And I've done that. So there are now lookup tables in my model so that we can, as the water fluxes in and out, we can add to and take away, and we turn off those boundaries just like I told you about. Was that any questions?
We have time for a question. So quick question on your model. You had more of what was a rectangle closer to. Since you're dealing with craters a lot of the time, why not a spherical cap harmonic?
It's on that. When I do it, we've put it on a spherical shot. I just wrap it back out so you can see it.
Okay, I'm talking about when you map it to it is still a circle on there, but it's described as a spherical cap instead. It's just slightly different. It doesn't have the hard edges.
I'm confused. Like I just display it as a square. I wrap it back out, but like when we solve it solved on a sphere.
Do you mean putting the sort of the pole of the spherical coordinate system in the crater, so it's more?
You could do that, and then it's bounded by a max and min polar angle. So it creates a spherical
Point is
cap.
we have multiple craters.
If you're mapping to others, yeah, I was just curious, yeah.
Yeah, I mean, the divergence in the gradient operators are in spherical coordinates
Okay,
when we solve. Which also makes all sorts of problems when you start calculating fluxes across spaces because the phase size changes. So
understood. It's not my area. We just in aerospace engineering, we go to spherical caps.
It's essentially what it
a
is.
small area.
It's an irregular domain spherical cap because we've removed the top and I just set a boundary condition on it.
All right, thank you.
All right.
Perfect. So our next speaker is Melanie Rowland. She's a 5th-year PhD candidate in astronomy, and she is a Finesse Fellow.
Great. Yeah, so today I'm gonna talk about some research I've done with a bunch of collaborators the last couple of months. So I'm in the astronomy department and I'm gonna be talking about the first detection of deuterium in an atmosphere outside of the solar system. And we found this on the coldest brown dwarf. So there's lots of geologists in the room. So what's a brown dwarf? A brown dwarf is an object that is substellar in mass. We typically think of it as between 13 and 80 Jupiter masses. The reason we define it this way is that if an object is between 13 and 80 Jupiter masses, it can use deuterium in its core early in its lifetime, and then it will deplete all of that deuterium, and then it cools just like a planet would. We find brown dwarfs in planetary or in protoplanetary disks forming like a planet, but we also see them in the field forming like stars. So they're very interesting objects for many reasons. One of the reasons is that if we are looking at field brown dwarfs, so brown dwarfs that aren't around a star, they are really great for atmospheric follow-up and atmospheric characterization because you don't have to worry about the contaminating stellar light when you're trying to analyze the atmosphere. And then I'll also say that we call brown dwarfs things that are between 13 and 80 Jupiter masses, but we think that the coldest brown dwarfs, these are cooling over time, the coldest brown dwarfs are expected to actually be planetary mass. Yeah, so atmospheric characterization. We've been doing atmospheric characterization of brown dwarfs and exoplanets for a few decades now, but it's only been in the last 3 years that we've been able to leverage new ground and space-based moderate infrared spectra to identify isotope log ratios. So what I'm showing on the top here are the isotope log ratios that have been measured in several brown dwarfs and exoplanets for both carbon isotopes and nitrogen isotopes. And so one of the goals of atmospheric characterization is identifying planet formation mechanism, how a planet formed, how a planet evolved, and how a planet migrated through a disk. And we're still at the very early stages of kind of mapping. We're able to make these measurements, but we don't really know what they mean. So we're kind of in the very early stages of figuring out why brown dwarfs have a higher solar-like 12 to 13 C ratio as compared to exoplanets that have a lower ratio. But what I'm talking about today is an isotope that we have decades of theory and modeling informing, and that's deuterium. So deuterium is the isotope of hydrogen. And the plot I'm showing here is the deuterium to hydrogen ratio as a function of mass. The gray line is the protosolar D to H ratio that we make for measurements of the interstellar medium. As we go from the interstellar medium into the disk, we see that comets are enhanced in their D to H ratio by almost an order of magnitude above the protosolar ISM value. And we attribute this to the fact that at temperatures below about 50 Kelvin, the preferred form of water ice is HDO rather than H2O. As we kind of expand this to the terrestrial planets, we see that they've inherited this D to H enhancement. We attribute this to the fact that they are getting most of their water from cometary impacts. And so Earth has a very similar amount to the comets. But you can also see that Mars and Venus are enhanced in their D to H ratio. And we attribute this to the fact that both Mars and Venus have some amount of atmospheric loss or atmospheric escape that's going to preferentially deplete them in hydrogen over deuterium. So you can see just so far in this plot that knowing deuterium abundance of a planet or an exoplanet can tell you about cometary or volatile transport within a system, as well as the subsequent atmospheric evolution of a planet. So going up in mass space again, we have the ice giants, Uranus and Neptune. They are also enhanced over the protosolar value, and we attribute this to the fact that a large fraction of their mass comes from ices, and lots of those ices have been accreted. And finally, within the solar system, we have Saturn and Jupiter. While we also think that they would have accreted this deuterium-enriched ice, their mass is dominated by the hydrogen, so we're not really sensitive to any deuterium enrichment. And then if you look going out of the solar system, looking into these more giant planets up to brown dwarfs, we'd expect that the brown dwarfs have a similar protosolar D to H ratio until you hit the deuterium burning limit at around 13 Jupiter masses, in which case your deuterium is quickly depleted. So how do we find deuterium? Deuterium is more detectable at colder temperatures. What I'm showing here are the cross sections of methane and methane's deuterated counterpart, CH3D. At the colder temperatures, you can see that the deuterated version of methane is kind of peaking out above the just regular methane. But as you go to hotter temperatures, the opacity of the deuterated species sinks below the non-deuterated counterpart. So we want to look at colder temperatures. And but also, so these are just for methane and deuterated methane. But when you're looking at an atmosphere, you have to consider all of the opacity sources from all of the species that would be absorbing. So here we have all of the species that we think would be absorbing in an atmosphere that's about 225 Kelvin. And you can see that at about 4.5 microns, CH3D pokes out as the most dominant opacity source. So we think that CH3D would be detectable at around 4.5 microns. And indeed, this is how we made the very first detection of deuterium in an astrophysical object, which was in Jupiter. So here is a spectrum of Jupiter taken at McDonald Observatory in the 1970s. And then this shows the P branch CH3D absorption in Jupiter. So looking out of the solar system, we know that we need to look for a cold object or we're going to target it in a cold object. Here's a color magnitude diagram showing kind of the coldest brown dwarfs that we typically call T and Y dwarfs. Those are in red. And then overplotted are just models that show the different effective temperature. WISO-855 is down here in the right corner as the coldest brown dwarf, and it's separated by about 100 Kelvin to the next coldest object we know about. This object has been the object of study for multiple JWST programs, and the data that we are analyzing in this program is coming from some GTO measurements that were taken last year and published recently. And this is coming from spectra that has a resolving power of 1,000, so moderate resolution spectra. So we ran a bunch of atmospheric models on the data. I use a technique known as atmospheric retrievals. We ran many models, and we find that this object does have deuterium. And what I'm showing here are plots of the residuals. So the error bars are in blue, and then what's plotted is our best fit model versus the data. And that's in orange. If we take our best fit model and then we set the deuterated methane abundance to 0, and then rerun the model, the difference is now in black. So we need the CH3D, the deuterated methane, in order to fit the data better. We also perform a cross correlation analysis and find CH3D at high SNR, so an SNR of about 20. And then we also did several different model comparisons using something called the delta BIC or Bayesian information criterion. For reference, a delta BIC of greater than 10 indicates a very strong preference for one model over another. And here we find a delta BIC of 59. So very, very strong preference for deuterium. We also wanted to make sure that our results were not model dependent. And so we ran many different forward models, changing basically everything we could think of within the atmosphere. So that includes including clouds, taking clouds away, changing the way that pressure or temperature varies with pressure in the atmosphere, and then different things with the chemistry, like including non-uniform water abundances in the atmosphere. And we find that our D to H ratio is very robust to a variety of model assumptions. So what I'm showing here are our posteriors for our D to H ratio. And then in comparison, we have that protosolar value of 2 × 10 to the negative 5. So our values are consistent with a protosolar amount. So this is this deuterium measurement of a protosolar amount confirms WISO-855 as a planetary mass object, which is in agreement with the evolutionary models that we have. What I'm showing here is the effective temperature versus age for 3 different planetary mass objects. So these are all below the 13 Jupiter mass deuterium burning limit. And so if we overplot the effective temperature of WISO-855, which is at about 250 Kelvin, all of the evolutionary models predict that WISO-855 would be a planetary mass, given how cold it is. And so going back to our plot from the beginning, we have all of our deuterium measurements, which we can now add YZ855 to this graph. And we expect that this is going to be the first of hopefully many deuterium measurements outside of the solar system in the years to come. JWST, we think, should be sensitive down to sub-Saturn mass objects. And then looking forward to the ELTs that will be coming online in the next like decade or so, they might be sensitive even to even lower masses, potentially down to like the super Earth regime, where we might be particularly sensitive to it due to potential lots of atmospheric mass loss that could enhance the D to H ratio. Extremely large telescopes. So the ELT, like the extremely large telescope, is supposed to be getting first light in 5 years. And that'll be it's like the 30-meter class telescope. So yeah.
2 more minutes.
Okay, cool. All right, so if I have 2 more minutes, so this is the picture a few weeks ago that we found deuterium for the first time, that it's a protosolar D to H ratio, and that we can potentially find this in other objects in the future. The complicating issue, which I was at a conference and everyone was saying, oh, if you do different reductions on the same data, you get different atmospheres. So I was doing my due diligence, and we got the same data reduced with a different pipeline, and we find massive changes in the flux between the 2 pipelines on the level of like 20 to 40%, even though the signal to noise is about of about 100. So you'd expect variations on a percent level, and instead the pipelines are producing very different data sets corresponding to 2 very different atmospheres, including the deuterium detection going away. I think we have several reasons to trust the original published data reduction pipeline. That one pipeline was made by the people who made the instrument, whereas the new pipeline is made by the people who are currently operating JWST. There are a few things, especially if we go to different data sets that have higher signal to noise, the deuterium pops back out again. But yeah, so we're still kind of working with the data reduction people to try to nail down what's causing the flux differences. So yeah, and with that, I will take any questions.
Questions? That includes if anyone online would like to ask.
Yeah.
Why would it be below the protosolar?
So I think the maybe a complicating issue here, the ISM values aren't exactly 2 × 10⁻⁵. They vary between like I think 1 and 3 values. It's possible if it's maybe more massive than we expected, closer like maybe 10 Jupiter masses. It's possible that it could have fused some of its deuterium before cooling so that it can no longer fuse all of it. But I think based on the temperature it is now, we expect a much lower, maybe between like 2 to 5 Jupiter masses. So we don't expect that to be the case.
You probably said this, but how do we know the protosolar? Is that just the sun's composition?
No, so the sun would have burned all of its deuterium already. We know it from looking at in the interstellar medium. So this is looking at the dust in the ISM, where we're able to measure that.
All right, thank you.
I have a quick question. I'm just surprised that we haven't detected deuterium before. What's the problem?
The problem, we've never been sensitive to objects that are this cold. So the in particular, so the brown dwarfs that we're looking at right now, effective temperatures of 300 to 400 Kelvin, they're emitting most of their flux at like beyond 4 microns. And so we only knew of a handful of these brown dwarfs when Spitzer, which was the last time we were sensitive to the infrared wavelengths, while it was still operational. So this is our first time getting spectra of objects that are below, I don't know, 700 Kelvin. So
Yeah, one more.
I'm sorry.
Yeah, no
No,
worries.
I have a kind of question that just came to me. Are there any prospects for like detecting deuterium for like a really young brown dwarf where like the deuterium hasn't been like burned yet?
yeah, so maybe, but based on models, it seems like they burn their deuterium really quickly. So if you get it within the first tens to 100 mega years, it might be possible. But yeah, the larger it is, the faster it will burn. So if it's, it's really most sensitive if it's between, I don't know, maybe 10 and 20 Jupiter masses, you might be able to catch it early enough, but I feel like there are complicating issues there. Our models do really poorly for low surface gravity, really young objects, so that could be another complicating factor.
All right, thank you very much. You got the.
Oh, yeah, let me get rid of that.
Other computer.
Oh,
No, it's yours.
Yeah.
Ah.
Does that work?
That'll work.
Does that work? Okay.
All right, so this is Trevor Wolf. He's a PhD student in the Department of Aerospace Engineering. And he tries to figure out how to make our sensor detect space objects and celestial objects better. So
Yeah.
leave it to that.
Thanks for that. Hello, everybody. My name is Trevor Wolf. Like Dr. Jen said, I am a PhD candidate in the Aerospace Engineering Department at UT. And today I'm going to be talking about one of my projects, which involves directly detecting substellar companions using autoencoder neural networks. So I should mention this is a collaboration with myself, Dr. Brandon Jones, who's in the aerospace engineering department, and then Dr. Brendan Buller, who is in the astronomy department here. So first off, I thought I would give a little bit of motivation for this talk. So in the exoplanet science community, we need a complete statistical census of exoplanet demographics in order to guide and test planet formation and evolutionary models. The vast majority of the census has been detected through indirect observables, so namely the radial velocity method and the transits. These methods are very sensitive to planets that are close to their host star, but are less so at wider orbital regimes. And that's where direct imaging comes in. So direct imaging is an effective tool to fill in this sample census from the outside in. But critical to direct imaging surveys are effective post-processing techniques. So how do we take these images that are mostly dominated by the flux from the host star and process them in a manner to where we can actually recover the point sources that we're trying to. So yeah, to touch on that a little bit more, the main challenge with direct image post-processing is we have this noisy image set that's dominated by the stellar flux and this quasi-static speckle noise. And we want to take that image set and transform it into some science product that you see on the right-hand side here. So this is a cool system. It's called HR8799. It actually contains 4 exoplanets. You can kind of see the outmost ones here. But then as you get closer and closer to the host star, for instance, there's one right here. You can see that it becomes very ambiguous what the actual point sources are that we're trying to resolve and what this speckle noise is. So yeah.
Point them out real quick, 'cause
Yeah, absolutely. Sorry. Yeah, so going from the outside in, one out here, one here, one here, one here. So yeah, it can be difficult. So yeah, so the method that we use for I should say the methods that we use for post-processing are inherently tied to the observing strategy that we use. So for direct imaging surveys, most commonly, we're using a technique called angular differential imaging. So with this, this method, it leverages the on-sky rotation that we have due to the parallactic rotation of an on-sky source to essentially spatially decouple that point source with this quasi-static speckle noise, which remains fixed in the image plane. So we use that decoupling along with, well, most commonly this technique called PCA, or principal component analysis. And PCA asks, what is an optimal low rank reconstruction basis, VQ here, that such that when we project a science image onto it and then transpose that image back into the original image space, we minimize some least squares costs or least squares function of the air. So this is so this works in a lot of cases, but there's some edge cases where it doesn't really work too well. So one of those cases is when we have insufficient field rotation. So when the parallactic rotation during an imaging sequence isn't sufficient enough, that basis can partially fit to the expected signal profile of that on-sky source. Moreover, PCA in general doesn't make any guarantees about the linear independence between the signal that we're trying to resolve and that basis. So in this work, we choose a different route. So instead of using this linear reconstruction method like PCA, we are effectively learning two nonlinear functions here, f and g, that again minimize some cost definition through their projection operation. So I guess one other thing to note, as I mentioned previously, this PCA reconstruction method doesn't necessarily guarantee that you're not going to fit to your point source that you're actually trying to resolve. Here we explicitly partition these image or hypothesized image patches into planet absent and planet present regions, denoted here by X and Y. So when we're doing this prediction, you can see that we're exclusively using that planet absent portion. So in doing so, we guarantee that we're not going to partially fit to that point source. So what are these functions f and g? So, I stated them very generally in the previous slide, but in this work, we're using an autoencoder neural network in order to parameterize those. So the function f can be thought of as the convergent portion of this neural network. In essence, it's doing something very similar to PCA. It's taking this high dimensional image and then transforming it into this lower dimensional convolutional feature space. The function g then, on the other hand, transposes those features back into the original image space. So a little bit about the training details of this algorithm. So construct, which is the name of our approach, was trained with 92 unique ADI sequences that were obtained from the Keck Observatory archive. From those 92 sequences, we extract 30,000 of these image patches for training. So yeah, the sample set is quite extensive. So I guess, how does this work in practice? So again, use my mouse here. It won't lag too much. So yeah, so we have this image patch where the central portion is masked out. Again, this is the planet present hypothesized region. This is the portion that we're trying to predict the speckle field over. To the right of that, we have our ground truth. This is what the speckle field in that portion actually looks like. And then to the bottom left, we have a prediction. We can see that, qualitatively speaking, the algorithm that we propose does a pretty good job in terms of predicting that speckle field in that portion. Now, what was interesting is when we inject this synthetic source off to the right here. So this is a 2D Gaussian profile that we inject over that portion. and then subtract the prediction from that, we can see that we can recover that point source quite well. So we use this tool in a very systematic fashion over an entire ADI sequence. So this might be a little hard to follow, but each pixel in a final science image will label a set of image patches throughout the entire ADI sequence, such that if it is contained in that first or in that pixel, then all of those patches will then also contain it. So I guess looking at this diagram to the left here, this kind of illustrates this a little bit better. So if there's a point source, say here in this patch here, then because of that parallactic rotation, throughout the rest of the ADI sequence, there's a deterministic set of patches that will also contain that source. So again, we're using this tool in this very I guess informed manner to then process an entire ADI sequence. How am I doing on time?
You've got about 3.5 minutes.
Okay, let's skip this slide. So here are some example reductions comparing our approach with PCA. And I apologize, it's a little small here. These look better in the journal paper, but I guess a couple that one thing I wanted to point out with this. So on the right-hand side, we're comparing the SNR or signal to noise ratio with construct, so our approach versus PCA. And for all of the planets in this HR8799 data set, we're achieving an SNR that is quite a bit higher than that we achieved with PCA. So that's cool to see. Here we're doing kind of a one-to-one comparison between PCA and our approach. So on the left-hand side, this is the maximal obtainable SNR for each of these processes. And for these cases, we can expect well, in this case, we're getting between a 25 to 75% improvement over those or for those samples. On the right-hand side, basically what we've done is we've fixed some design parameters for both PCA and construct, and then we applied it to 30 unique point sources. And then in this case, we're finding that for about 2/3 of the cases, we're seeing a improvement in SNR over traditional techniques. So to wrap up a little bit, I guess the main takeaway with this work is that constructs to our approach demonstrates the capability of deep learning to enhance post-processing methods in direct high contrast imaging. Particularly in this work, we use a convolutional neural network and train this network on an extensive library of reference imaging data sets, and showed that we could accurately reconstruct the speckled field at the location of a hypothesized point source. We applied it to real nurture data sets and showed that for 2/3 of the cases, we could improve the SNR over traditional PCA processing methods. So with that, I'll take any questions. Yeah.
How do you quantify the signal and noise
Yeah, so
between the two techniques? I guess?
right. So what we do is we take kind of like a circular aperture around the location where we know a point source is, and then calculate the RMS of the speckle noise there. And then that serves as the noise, essentially. Yeah.
In both.
Exactly. Yep.
Great talk, Trevor. I'm wondering, do you have a sense of, how the comparison between the recovered construct signal noise and the PCA or more traditional or the signal noise from more traditional ESF suppression algorithms? Do you have a sense of how the kind of difference or benefit of construct scales with, for example, like different frame rotation levels or different kind of planet locations or separations?
Yeah, that's a good question. So we touched on that a little bit here. So here in this particular example, we're plotting in the color the number of frames in an ADI sequence. So I guess for that case, we do find that there is some correlation between the improvement that we see with construct and that particular variable, but you bring up a good point. It would be nice to kind of quantify some other aspects that might be important with that as well.
For ADI, we're using ADI.
Mhm.
And I guess like said, the number of frames, over how is it, can you get all of the information you need in a single night, or do you have to wait? Over time in order to get like the different angular. Yeah, like,
Well, so are you are you speaking in terms of training it or testing it?
or I guess in terms of, so you're playing from the National Archive.
Mhm.
Are those observations of the different systems, are those observations that were done in a single night that you could use?
No.
Or is it taken over time, like 6 months?
Yeah. So in terms of training, we use like basically anything that's on Keck Archive. Yeah, it definitely doesn't have to be over like a single night. Yeah, but you know, in terms of processing, like how we actually, you know, create it, say, plots like this, yes, these are data sets that were collected over like a single night. Yep.
So I guess, do you have a sense, because you're masking both companions at, then also using this new neural network autoencoder, how much of the advantage, well, maybe for the first question is, are also doing the masking during the more classical PCA? Because I think a lot of people don't. They just rely on sheer number of frames to take care of it. So
Right.
do you guess how much of the advantage comes from doing the masking versus using this different autoencoder versus more classical PCA techniques?
Yeah, that's a good question. I don't have a great sense of that, to be honest. You bring up a good point, because for the PCA reductions that I didn't necessarily max those out as well. So you know, it could be the case that you know, if we applied masking to our PCA reduction pipeline, we might not see as much benefit, but I'm not positive about that.
Presumably you have to do a separate run of the whole thing for like every pixel of every target though, so it's like very computationally intensive.
It is, and
I'm
that's
hoping like.
and that's
why
what,
I think people are
yeah,
afraid of
that's
more.
and you know, that's precisely what we're doing with construct as well. So it takes quite a bit more time than just like a PCA approach.
That currently went out.
Whoops.
Do you have a related question at this time?
I think there is.
I guess you're doing this with ADI data sequences. Have you tested it with RDI, reference differential imaging, where you might even just have just a few snapshots to get them started? But
Yeah.
try doing this and speckle noise.
Yeah, I haven't done that now, but that would also be really cool to try.
Yeah, I have another question at this time. So along kind of similar lines to the kind of scaling of the construct advantage with different parameters. So NERC2 just went through a direct detector upgrade where it's saving every single cohat. So a sequence, instead of having like 100 frames, right, like might have like 10,000 like realizations of the PSM. Do you have a sense? Obviously, it would take like a gazillion like hours to run construct of those sequences. But like, I don't know, like, do you think that there would be like mileage from like bonus mileage from like running those on the sequences where you have the same amount of frame rotation,
Yeah.
we have like way more frames?
Yeah. That's really interesting. I could see a case for there being some, maybe not, you know, construct in this form right now, right? But I could see how that additional information, or that I guess additional temporal resolution that you get through that might be useful for that. I'm not exactly sure how that would work though.
All right, well, thank you very much.